Okay, hi, my name is Cyril Zhang, and today I'm going to talk about how a cheap vibration sensor can be fooled into reporting fake structural tremors and a way we can do to fix these issues. So, to talk more about the problem itself, um, let's imagine this scenario. Imagining we're trying to install a vibration motor in a building that has fans, machinery, and motors running in the background. Now, our sensor is designed so that it's supposed to detect slow structural motion. Like, let's say, detecting if the building itself is shaking, something that would actually prove that something is actually going wrong. But the building also has a lot of heavy machinery running in the background. Like we said, the motors, the fans, or whatever. These are vibrating at a very high frequency. And so in this case, if our sensor samples too slowly, these high frequency components don't just disappear. And oftentimes they actually fold back into the data and show up as low frequency tremors. In this case, our sensor would think that the building is shaking when it actually isn't, and just because it's just background noise from the machinery. So to start, let's talk about the model we're going to look at. So we modeled the vibration into three parts. First, we're looking at the structural modes, these low frequencies. Here we have a 4.5, 12, and 25 hertz signal. In these low building motions, these are the values we actually care about and the ones our sensor needs to detect if there's any big jumps. The other ones is going to be our transition impact. In this case, at time equals 5 seconds, we're going to simulate something like a door slam or someone drops something, like a sudden sound, sudden frequency that also, but also decays exponentially. And the last is going to be the machinery noise at a high frequency, in this case, 91 hertz and 125 hertz. These are the ones that we don't actually care about and will actually cause our problems. So we first start by plotting these out using Matlab. And here we can see our signals sampled at 200 hertz. We will treat that as a continuous time. On the right, we can see these signals, the slow structural bands, the sudden ring, and also these high machinery bands. On the right, you can see the sampling frequency by only looking at structural frequency. We can see these fairly low frequency signal. And then if we add the impact, we can see that at 5 seconds, there's a sudden change to the signal and then slowly goes back into just the structural. And if we add all three with the machinery noise, we can start to see these very high frequency, very noisy signals. So first, let's predict what would happen if we just sample it directly. So before we run on lab out, we're going to do some predictions. So using the Aliasing formula, if we take the mod of f over s and then fold it if it's above the Nyquist. So at 500 frequency, everything is very safe. It's higher than what's needed. At 225, we are now on the borderline. At 200, it starts flying to aliasing, but still manages to stay fairly above the structural band. But 100 hertz, that's where things fail. The 91 hertz falls into a 99 hertz, and the 120 hertz signal falls into a 25 hertz, which both actually lands it inside the structural band, which now becomes a false tremor. So let's see if our predictions are right with MATLAB. And unfortunately, MATLAB actually kind of confirms this prediction. So on the four plots, you can see that at 5 frequencies, there's not everything looks basically the same. But if we keep decreasing sampling frequency into the lowest graph here at 100 hertz, we start to see these new aliasing signals that aren't even the structural bands. They're inside the structural bands, but they're actually not our structural signals. In this case, are these machinery signals being disguised, and our real sensor would actually report these structural problems, and then even though they're just machine components. So these would be completely wrong. So before we talk about how to fix this, another thing we can talk about is how we can resample these sample signals and make an issue with this. So there's two main ways. One, we use a zero order hold where we kind of gives us the staircase, or we can use linear impolarization, which gives us a more smooth result. But the problem is that both result, if our sample frequency is corrupted, our final signal will be corrupted no matter what. In this case, it kind of shows that since our sample has already caused aliasing, if the data is already corrupted at sampling, both reconstruction would also be corrupted. So how can we actually fix this corruption issue? Well, one way is to design a sampling filter before everything. So if we don't want to actually change the sample frequency, what we can do is design a low pass filter. In this case, at a 45 hertz cutoff. If you can see that the impulse response is about shape from a Hamming window, and the frequency response is flat and around 4 hertz and drops to around negative 60 dB at around 90 hertz. So the trade-off is that we want to design these filters to, first of all, not be too low to actually cut off our structural mode, but also not too high so that it doesn't cut off the machine parts. And by doing 45 hertz, we can actually see a really good result where essentially the high machine filters are being filtered out and only the low structural signals even remain. And with the machinery parts on, even though we sample with a low frequency and before which didn't work, now the final result is still trustworthy, which kind of shows a way to get a trustworthy result without having to actually just increase the sample frequency.